How's it going, everybody? This is Just Cross. I am back with another video, and today we are continuing my chapter by chapter review for my proofing exam that is Saturday. And so yesterday, if you did not see, we covered set theory, which was a whole introductory, very basic set theory. And now today we're covering chapter 2. And chapter 2 is a lot less broad than chapter 1. Chapter 1 was literally just everything set related to get us some fundamentals, some basis for what we can do in the future. And it's this, at least at first. We are doing, I can now see that there's just no, it's not cross the T. Chapter 2, we have Cartesian products, we have relations, and we have functions. And that is basically the entirety of chapter 2. And functions in particular is really important in general for chapter 3, as well as throughout chapter 2. Specifically with functions establishing bijections, which I've discussed in chapter 3, in my chapter 3 review, but it's just important in its own right because so many things can be defined by a bijection, or by a bijective function. But we're going to start with Cartesian products. And Cartesian products is, here, let's just get to a new page. Cartesian products is, we've defined, let me write it a little bit faster before I start talking. We've defined, A plus B, we've defined A minus B, and we've even defined A circle plus B, the symmetric difference. But one thing we haven't defined is what happens when you multiply sets, and Cartesian products do exactly that. We can say that the definition of a Cartesian product in its own right, or yeah, A multiplied with B, sometimes I'll just call it cross because okay, everything's deciding to be really loud outside while I do this. Give me 2 seconds. Riveting. Anyway, so sometimes I'll just say A cross B because I, did cross products a lot. But basically we can define A times B as the ordered pair little b with the property that A is in A and B is in B. Now what do I mean by that? And I can just immediately show you with a small example just because I think that's the easiest way to define it. So let's say A is the set 1, 2, and we have B is the set 3, 4. Now, what do we want, or what do we get if we do A cross B? Well, we get the set containing all ordered pairs with an A in A and a B in B. So, you get 1, which is an A, and then you get 3, the pair 1, 3, which is 1 is an A, 3 is in B. You get 1, 4, 1 is an A, 4 is in B. And then you get 2, 3, 2 is an A, 3 is in B. 2, 4. 2 is an A, 4 is in B. And that's your whole set. That is your Cartesian product just in a nutshell. And you can define, I believe there's a strict definition, is basically the amount of elements, the cardinality of A times B is equal to the cardinality of A times the cardinality of B. That's kind of a no fucking brainer, I think. Like, that's pretty obvious to me. Like, cardinality here, 2, cardinality here, 2, you got cardinality of 4. Woo, riveting. And if B had another element, say 5, be 3 times 2, 6, and you'd have 6 elements in A times B, or in A across B. But that is in pure essence what a Cartesian product is. And it's very useful to define because we can use a lot of proofs with it. And so we can basically, what is attempted is to more concretely define just what an ordered pair is. And so we can use the definition basically if that A, B, C, D are all elements and we have the 2 ordered pairs A, B, and then C, D, we can say that if A, B is equal to C, D, that implies, or that is equivalent to saying A is equal to C, B is equal to D. And it's just some set theory. Basically, I have in my literal notes that I took while I was in class, I have set theory wacky stuff. Order implied due to A appearing in both elements. The proof is really kind of long and kind of weird. And then we can also just say that if AB is equal to BA, then A equals B, because again, kind of no-brainer. And that'll be important with properties of relations as well. Here, let me just get to... So basically, the Cartesian product is their set. I've already defined this. I don't know why the notes are kind of out of order. But their Cartesian product is the set of all ordered pairs, where A is an A, the little a, and then B is an B, the little b. And then if A has m elements and B has n elements, then A crossed with B has m times n. But the Cartesian product is not associative. And so what do I mean by that is basically this A crossed with B cross C is not the same as A crossed with B cross C. Excuse me, because these ordered pairs would come out to be the ordered pair A, B, C, and then this would come out to be A, B, C. I hope that like the little inflection in my voice changed how you understood it if you're not like watching. But we have some theorems here. We have some quick theorems to go over, or just some properties of 2 and 3 sets with Cartesian products. So if we have A, B, and C, if A, B, C sets, we have 1, 2, 3, 4. I'm probably going to write bigger. Whatever. So we have that A union B crossed with C is the same as A cross C union B cross C. Which that I think, that again, most of these formulas, I would say, are very, very similar to the formulas that we discussed with sets, and how like a lot of them can commute, and I think that's why it's also very, or like also associative, and so I think that's why it's very important to note when something is just not associative. And we have the same thing with the intersection. A intersected with B cross C is equal to A cross C intersected with B cross C. And then the third one, I think, is also kind of obvious if you see it. A minus B cross C is equal to A cross C minus B cross C. And then if we have that if A is not empty, and B is also not empty, so basically there's no trivial case. B is not empty. Then we have that A crossed B is equal to B cross A, is equivalent to saying that A is equal to B. And that, again, kind of follows, I mean, from the, that makes sense. Like that just makes sense if you know the definition, considering that A cross B would be A, B, where A is an A, B is in B, and then this would be B, A, or B is in B, B is in B, A, and A, and we know that A, B is equal to, in this case, we can just say C, D, then A is equal to C, D is equal to B, because I wrote B wrong. And we can just use that logic here. We have A is equal to B, B is equal to A, da 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 da. That, like, you can make a proof for it, you can make a rigorous proof, but I think it's kind of intuitive to see that. And then if we have, all right, this one's a little bit weird. If A1 is a subset of the power set A, and then if B1 is the subset of the power set of B, then A1 times B1 is an element. Yes. of the power set of A times B. That's weird. And then to show that, you'd basically have to show, or yeah, what? And then if A and B have, oh, there's one more. Shoot, I didn't even see the sixth. If A and B both have at least two elements, then we can say for certain that the power set of A crossed B does not equal A1 times B1 with A1 excuse me, be a power set of A, B1 is in the power set of B. We can say, here we can move it up. Do 6, continued. So we can actually say that A1 cross with B1 with A1 as an element of PA and then B1 element of PB, that is a proper subset of the power set. Proper subset. And then we can kind of go over a terminology thing real quick because it is important in specifically cardinality, actually, which is I'm kind of surprised why I did not go over it, or at least the terms. We have like, I don't even know if they're official terms, loose versus strict inclusion. So basically, proper subset versus just a normal subset. It's going to be less than, greater than, versus less than, or yeah, less than or equal to, greater than or equal to. Basically, strict inclusion. I did it backwards too. This is, I'm just, whatever. We're going to correct that because that's going to bother me. Because the one on this is loose. Strict versus loose. This is strict, these ones, because there's no opportunity for them to be equal. Basically, it's very strict about it, is that it is properly defined. There's no ambiguity. That's kind of important, again, for cardinality, especially with Schroeder-Bernstein, which, fuck that man, fuck Schroeder, fuck Bernstein. We don't like them. And so, let me see, I forgot how long these proofs are. Proving Cartesian product stuff is ridiculous. We can prove 5 though. Real quick, we can prove 5 because why not? I don't see the problem with that. All right, so we're trying to prove number 5 that I wrote, and let me rewrite it just so you know what we are trying to, or just to say what we're trying to prove, which is basically A1 is in the power set of A, and B1 is in the power set of B. Then A1 crossed with B1 is in the power set of A crossed with B. And also, I want to note, because I literally said it like 5 minutes ago, but like I'm saying crossed, it is not the cross product. If you know what the cross product is, it is not the cross product. It is just, I am lazy to say times or multiplied. I just think crossed flows better. But that is neither here nor there, especially because how the fuck would you take a cross product of a set anyway? That's not my business. Okay, so basically, the proof is pretty short, which is why I chose to do it, because writing a very long proof on a short MS Paint would be very annoying. So we have the A1 is in the power set of A, which is equivalent to knowing that A1 is a subset of A. And you can say the same thing for B1, knowing that B1 is a subset of B. And we need to show that A1 times B1 is a subset of A times B. So we can start showing that by saying that XY is an element of A1 times B1, which is, again, equivalent to X in A1, Y in B1. All right, we following? And so we can replace it by saying A1 is a subset of A. B1 is a subset of B. Again, which implies that, or not even that. Don't even need the 1. It's just X is in A, Y is in B. Which X is still in A, Y is still in B. And again, that is just equivalent to saying that XY is in A times B. So, and then our consequence is, of course, A1 times B1 with the property A1 is an element of P of A, B1 is an element of P of B, is a subset of the power set of A times B. But that's basically all you really need to know right now. Cartesian products come back in a weird way with cardinality, talking about cardinality of Cartesian products, specifically of like n times n. Like, what is the cardinality of n times n? Spoiler alert, it's just the cardinality of n because they're both countably infinite. However, that's spoilers. That's getting ahead of ourselves. Cardinality, again, is like the thing I kind of know. I kind of know what we're talking about there. But enough about Cartesian products. It's time to talk about relations. That is the second of our three starring actors in this chapter. And a relation on the set S is a subset R, or is a subset R. So you can do a relation on the set S, on the set S, or on a set, semantics, on a set S is a subset R, which is a subset to the Cartesian product with itself. So basically we have, what does that mean? We have x, y, who are both in S. It means that x related to y, that is our notation. And that means that x, y is an element of the relation. And then if x slash y means xy is not a member of the subset. It's not in the subset R. And then we can define, I'm going to do a new page for it just because it is a lot of writing and actual mathematical terminology. And so we can call a relation different things. So we can call it, oh, that's just a bad R, even for my handwriting, reflexive. We can call it symmetric. We can call it anti-symmetric, because of course we can. Then we can call it transitive. Now, what does that mean? And now pretend we have three elements, x, y, and z, because we're going to need them for transitivity. Reflexive basically just means, does x relate with x? So basically, is x in R? Excuse me, for all x in S. That is reflexive, like reflexivity. So like if you have like 1 is reflexive. Yeah. Symmetric, we have if x relates with y, that implies that y also relates with x for all x, y in S. And we can rewrite it better, basically saying xy in S implies that yx is in S. Okay, so basically if it was symmetric, then we can say that if we had 1, 2, then that implied that 2, 1 is also an element of S. Let's delete that. And then anti-symmetric is a little bit, anti-symmetric's kind of weird. It's basically saying, and we start with a clarifying statement for all x, y, and s. X relates to y, and y relates to x implies, or yeah, only when x is equal to y. So basically, again, it'd be like, have to be like 1, 1, to where like 1, 1's reflexive, 1, 1 is anti-symmetric, or is symmetric, basically because it exists, x, y, and y, x are there as well, and then it's also x equals y. And then transitive, we have basically for all x, y, and z in S, we can say that x relates to y, y relates to z, it implies x relates to z. So that again, like 1, 2, and then 2, 3 exist. If it was transitive, then that would automatically imply that 1, 3 is also an element in S. Because this is your x, this is your y, and this is your z. So 1, 3 would also automatically be in S if it was transitive. Excuse me. I have to get some Gatorade. And we can do a quick example or two just to think about it a little bit. So we can say our set is 1, 2, 3. And so our R, we can do R1 because we're going to do different R's. Our set is 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3. So what is that? Off the bat, it's reflexive. It's not symmetric. And it's anti-symmetric, and it's transitive. We can see right here, we can see the transitivity right here. We can see, reflexivity. Or we can see that it's reflexive because for every x we have, we can see x relates to itself. Oh, here, let me use a different color. So we can say that the transitivity is the blue. And then we can see for every x we have here, we can see that it is reflexive on itself, and especially x here, and it reflects on itself. And then symmetric is not, or we are not symmetric. Because basically, we have 1, 2, but we do not, 2, 1 is not an element of R1. And then obviously 3, 2 is not an element of R1. 3, 1 is not. That is why it is not symmetric. And then anti-symmetric, the only cases where x relates with y and y relates with x are, again, I'm not using, here, that was symmetric. Let me use a different color again to display. Basically, for anti-symmetric, x relates with y and y relates with x are the only time in R1 this happens are in these 3. And for each of them, x is equal to y, maintaining our anti-symmetricity. And we have space for one more, so we can do R2 is equal to 1, 1, 2, 2, 3, 1, 1, 2. So it is not reflexive, it is symmetric, it's not anti-symmetric, and it is transitive. So why is it any of those? It's not reflexive. I'll choose green. It's not reflexive because, wow, x equals 3 is an element of an xy, which is in R2. 3, 3 is not an element in R2. So it's not reflexive. And then the next one I can look at, it's not antisymmetric. We have that x relates with y, and y relates with x. No. We do have oh. Wait, what? I think I wrote the example down wrong. Cause yeah, I did. Hold on. It's whoops. And because that me writing it down wrong means that there's a different implication for why it's not reflexive. It's 2, 1, 1, 2. Whoops. Okay. And also in general, so it's not reflexive still. It's still not reflexive. And we could talk about it for a different reason, better reasons, because you have our set 1, 2, and 3. All elements in S need to be represented and need to show that they can relate to themselves to be for the subset to be considered reflexive. We have 1 reflecting upon itself, we have 2 reflecting upon itself, but 3, 3 still is not an element of R2, which means it's not reflexive. Here, let me grab that color. And then symmetric, it is symmetric because 1, 2, and 2, 1 are elements of R2, and that's the only 2 elements that aren't the same. It is not antisymmetric because of this. 1 does not, let me, new color. 1 does not equal 2. So x relates with y and y relates with x, but x does not equal y. And then it is transitive. But why is it transitive? So this, the transitivity, is a funky bit of logic, and it's basically if the assumption is not satisfied. So for the assumption of transitivity, the assumption needs 3 elements. And so like in the first one, it's 1, 2, 3. You need 3 elements so that the assumption can be satisfied. If the assumption is not satisfied, and this is kind of important, so I can like, if the assumption is not satisfied, then the implication is true. Now, what does that mean? The implication is true. So basically, again, you have to assume that there's 3 elements for transitivity to exist, and for the bare minimum is 3 elements to show that something is transitive. We do not have 3 elements here. There's 2 elements, 1 and 2. That's it. That's the only x. There's not enough elements to try to prove or disprove transitivity. So in this case, the subset is transitive by default. It's a really weird kind of logic, a logical sort of thing. And we can say for any set S, the Cartesian product and the empty set are both relations. This is just in every general case for a general set S. And then Cartesian product R equals, here, this is actually kind of, again, important, and then I will make a new page again to continue talking. We have that if S is equal to R cross with R, this is reflexive, it's symmetric, it's not it is not anti-symmetric. Not anti-sim, and then it is transitive. And then if S has here, if, perfect. And then we have our empty set, and it is symmetric, it is transitive, it is anti-symmetric too, not reflexive. If S is equal to the empty set. So that's some riveting stuff. Okay, that is riveting. God, we still have a long way to go too, and we are already 30 minutes in. Whoa, this is gonna be a longer video than yesterday. And we've done like one proof. But that is okay. That is, we rock, we roll. Now let's get moving to more relation fun stuff. Okay, because we're gonna dip our toes into modulo in a second, which is interesting on its own, right? And now we can say, under their definition, a set S with with relation R on S is called, we have partially ordered or totally ordered. Now, what do they mean? It is if R is reflexive, anti-symmetric, and transitive. And then totally ordered is if R is partially ordered and for all x, y, and s, x relates with y or y relates with x. It's called the comparability condition, apparently. So that's cool. So we can do an example. So we have S is equal to R, which is the whole real numbers. And we can say it with R, small r, being x, y in R cross R, with the condition that x is less than or equal to y. Excuse me. So we define x related to y by x less than or equal to y. This is a total order. X is less than or equal to x by definition, so that is reflexive. We have that x is less than or equal to y, and y is less than or equal to x, which implies x equals y, which is anti-symmetry. We have our transitivity. If x is less than or equal to y, y is less than or equal to z, we imply that x is less than or equal to z, which is our transitivity. And then comparability, either for every number, x is less than or equal to y, or y is less than or equal to x. So that is a total order. Give me 2 seconds. Okay, now we're getting into complicated stuff, kind of. And so we have the wire on my fucking tablet, or the tablet I am using, started brushing on my leg, and it was the most terrifying 2 seconds. I thought like a big ass bug was on me. A relation R on set S is called an... Okay, hold on, let me write this better already. It's called an equivalence relation if R is reflexive, transitive, and symmetric. All right. And with equivalence relations, it's important to note just the differences. These requirements are different than the partially ordered one, namely the requirement to be symmetric. So you can obviously say an equivalence relation is not the same as a partial ordering. If somehow, or if an equivalence relation was also antisymmetric as well as these three, then you can say it is also partially ordered as well as an equivalence relation, but that's just that is a side note to make. And whoops, sim, transitive, reflexive, and it's denoted by the tilde, x tilde y, for x, y, both in s. If, we can also just say if x relates to y and r is an equivalent relation. So what is this used for? So I can give an example real quick. And sorry if like I'm sighing a lot or like taking a lot of deep breaths. I am getting over being sick and I have not exerted myself as often because I am sick. So that is why. So we have x is or s is equal to the set of all integers, and we have r is the set x, y, which is in z times z, with the property that x minus y is even. Now, is this an equivalence relation? We have to check the three properties. So we check reflexivity. X is reflexive with x for all x in z. And is this true? Yes, because x minus x is equal to 0, which in normal standard mathematical conventions is in fact even. Which is in fact even. So now we check symmetry. R is symmetric. So we have to check that x being an equivalence relation. We know that that implies that x minus y is even. And we know we can redefine even, or we can define even using a definition where even means x minus y is equal to 2z for some z in z. And we can flip the script. If we have y relates to x, we can say that y minus x is equal to negative 2z with a z in z, which, I mean, yeah, it's the basically those are the same. I don't know how else to like say it better. Like those are the same. And then for transitive, we have to show that that and that implies that z is related, or is an equivalence relation. So we know that x minus y and y minus z are even. So we can say that x minus y is equal to 2a, y minus z is equal to 2b for a, b in z. And so we can do x, that's higher than I wanted to write it. We can do x minus y plus y minus z is equal to 2a plus 2b, which is equal to 2a plus b, which implies that x is in fact related to c. But on to a new definition. That was just a little quick example. And we can say, or we have a definition now. For a fixed, I'm going to write out the whole thing. For a fixed m in n and integer here, and then a not fixed. We say a is congruent to b modulo m if, m divides a minus b. It's written as a is congruent to b mod m. Basically, it's also saying there exists a z in z such that a minus b is equal to m times z. And so we can just do like 2 examples. 3 is congruent to 7 mod 2. This is our a, this is our b. -4 is in fact divisible by 2. That gives you -2. Therefore, it is congruent. And then we can do like 5 is congruent to, how about 15 is congruent to 3 mod, 6. Because you can do 15 minus 3, 12, that's divisible by 6, which equals 2, which is, in fact, cool. It's cool. It's cool. It has some divisibility rules, I guess. It's nice to have. It's good for dividing. It's good for making subsets of integers specifically. And we say m is the modulus for it. Let me just let's go to a new one. And again, we can say, sorry, I'm scanning through my notes. And then knowing that, we can say, for any given modulus, and I'll add the 0 there. That basically just means including 0. That is just 0 unioned with 1, 2. That's just, I don't know. You can do mod 0 or no. Because 0 no, don't worry about it. Just kidding. Just kidding. Don't. I'm confusing myself with the semantics of it. We can say that an equivalence relation is for an ordered set AB, which is in Z by Z. That is, hold on, I'm reading, Wait, no, I was reading the right thing up to a certain point. Such that A is congruent to B mod M. And this is an equivalence relation. Not check, let's do an exclamation point. That's an equivalence relation. And we can do a proof. And a proof I will. So I need to show that that is reflexive first. And so observe that we can say A is congruent to A mod M. A minus A is equal to 0. 0 is divisible by everything. Which makes it okay. Which implies that A is congruent with A. Mod M, or, that just means that A relates with A. which is cool. And then I'm going to make a new page to prove the other two. We need to prove that it is reflexive. Oh, let me get proofing red. Is reflexive. And we need to show basically, to show for all A, B, and Z, A being related to B implies that B is related to A. So how do we do that? Given that we have A is congruent to B mod M, that again implies that there exists a Z in Z such that A minus B is equal to MZ. Okay, so basically that also implies there exists in Z a Z in Z such that B minus A is equal to negative MZ by or M times negative Z if you pull the negative out with Z still in Z, which that is a definition that you can say is B is congruent to, whoops, A mod M, which is saying that B is related to A. So we have A relates to B implies that B relates to A. Very nice. And now we show transitivity. And I do not have enough space because I chose to write big. Okay, so we have to show here transitivity. I have to show for A, B, C, in Z. We have A relates to B, B relates to C, implies A relates to C. Oh, that's an awful. So how do we do this? So we know that there exists a Z in Z such that A, out here, Z1, A minus B is equal to M of Z1. And we know that there exists a Z2 in Z such that B minus C is equal to M Z2. Okay, so we can do A minus B plus B minus C, which is equal to M Z1 plus Z2, which this is still an element of Z. And so we know that M divides A minus C, which, i.e., that is that A is congruent to C mod M, which implies A is congruent to C. And that is our proof, because that proves it is transitive. Wow! Neat. And so now we cover something new, or something very much related to this. And it's something I never actually completely understood. And it was by far the worst thing that I did on our exam, the second exam that I did very poorly on. So we can say, maybe I'll do better on it the second time. Oh God, that is an ugly ass Q. The equivalence class of X in S with respect to that is identified as X is equal to, oh, that's, nope, a set bracket S and S such that S relates to X. What does that mean? Okay, so I can do an example immediately. So say we have, if this is congruence, the congruence modulo congruence mod 2, then we have when x is equal to 0. We have s is an element in Z to where s is congruent to 0 mod 2, which basically is just s in Z, s is even. And then we have 1, which is s in Z such that s is congruent to 1 mod 2, which is s in Z, s is odd. So there's only, there's only 2 equivalence classes, and we know, and we state it in a rule or theorem later, basically, whatever m is, you have m congruence classes. It's just going from 0 to m minus 1. So m is 2, so we have 0 to 1. It as many congruence classes. So like if we had 4 congruence classes, it would be 0. Or m was 4, it'd be 0, 1, 2, and 3. Excuse me, for example. That's cool. And here, related to this, we can make a note, basically, which is in that specific case, the equivalence class of 0 is equal to the equivalence class of 2, which is equal to the equivalence class of 4, which is equal to the equivalence class of like -2, of -4, ... It's equal to every equivalence class of an even number. It is all evens. And the same thing with 1. 1 is equal to the equivalence class of 3, is equal to because they're infinite. They are infinite classes because it's every even number. So it'd be 2, 6, 8, and then 0, -2, -4, and we know that Z is the disjoint union of, it's basically just saying it's the set of even integers unioned with the set of odd integers. Wow. That it makes sense. It makes sense. But anyway, we need to continue on with the content. Just let me sip my water and check how long I've been recording. 53 minutes. And we're not even at functions. Oh my god. This might have to be a two-parter, honestly. Yeah, maybe. Because I got... Let's see what day this was written. Yeah, I got a whole month to do. I said it in the last video. This one's definitely going to be the longest. Okay. So we get to the next theory. If tilde is an equivalence relation on S, and then x, y in S, that is just a 5 in S, we can say that if the intersection between 2 equivalence classes is not empty. I don't have... What the hell? I don't think I finished this. I don't think I finished the definition. Because I just have... It implies that x intersects y. Interesting. Well, whatever. We're going to continue going. That's ominous. Okay, and then we're going to bring back indexed family of sets, specifically with equivalence classes, by saying we have assume that tilde is an equiv relation on S where it does not equal the empty set. And that we have, excuse me, indexed family of sets xi, I and I, is the indexed family of all distinct indexed family of all distinct equivalence relations with respect to tilde. Then we can actually say that this hunk of junk in here, I and I is actually a partition. Partition of S. That's cool. So we can actually just keep going. Sorry, it's been a long day. I've been awake like 6 hours or something. Okay, I rewrote the theorem. Can skip that. Yeah, and we define this in our precisely m distinct congruence classes modulo m, namely 0 to m minus 1. Yeah, the set of congruence classes modulo m is denoted as z sub m. So we can say that z sub m is equal to the set containing 0, 1, m minus 1. Which is, that's fair. One can define an addition and multiplication on Z by basically saying A plus, and the same thing with times. Just keep accidentally doing the floor. Keep doing the floor function sign rather than the ceiling. Useless. I don't get why. And this is a tease for a later math course, but basically, are those operations well defined? Yes, but we don't have the proof because it's too advanced for us, and this turns Zm into a commutative ring. And I don't know what that means. I'm going to learn that next semester, and I'm not excited. I'm not going to lie. I'm not excited at all for it, in any stretch of the imagination. Don't think I am. Okay, and now we have if. We have our indexed family of sets yet again. I and I is a partition of S not equal to the empty set. And if we define if x related to y is, or x equivalence relation to the y is defined, What? This is so like unnecessarily worded. Okay, here I will write it word for word. And if we define x tilde y for x, y, and s by x tilde y, if and only if there exists an I such that x, y is an AI. Oh, oops. Then tilde is an equivalence relation on S. And the AI are the equivalence classes respect to tilde. Huh. Okay. So basically we can do an example real quick because that's a long wordy motherfucker that I kind of had to think through. Basically, if we define it and then if there's an I such that they exist, then the equivalence relation itself exists, and that AI or the AI themselves are the equivalence class. Jesus, equivalence classes. Excuse me. Okay. So for example, we have S is equal to 1, 2, 3, 4, 5, 6. We have I is equal to 1, 2, 3. So we have A1 is equal to the set 1. A2 is equal to 2. Oh, 2, 3. And then we have A3 is equal to 3, 4, 5. Or no. 4, 5, 6. What is the associated tilde? And basically, we can show, or we need to have one relate to 1, one relate to 2, one relate to 3. Or we first off, actually, before we even try to do that, we need 2 relate to 2, all the way up to 6 relates to 6, because that's the AS Paint stores images as you work on them. However, there's run out of space to do so. You can still save the current image. No, I don't think I will. I guess it's JS Paint is getting fucking tired of me. We need to show that, as well as we need to show for every 2 relates to 3, which we need a 3 relates to 2, 4 relates to 5, 5 relates to 4, 4 relates to 6, 6 relates to 4, etc., etc. So we basically, and we can use the original definition of a relation as a subset of S by S to show that this entire equivalence relation is just S by S. Because for 1 to 1, it's 1, 1. We have 2, 2, up to 6, 6. And then we have, 2, 3, 3, 2, and onwards to get the whole thing. And I'm gonna stop right here for today. I will do the rest. I will upload the rest of this chapter, I guess, tomorrow, because I told you it would be a fucking long one. And functions are the longest part, actually. So what do we still have left? Got functions. That's it. We got functions left. And all of their uses, basically, functions, their properties. So like injective, bijective, surjective, their domain, codomain, image, pre-image, stuff like that. We got a while. We got a lot of function stuff to do because we can, and then just to show f from a to b, or or they basically he told us that this could also be written like that. But that's for inverses. Fuck, that's a big one. Inverses, and onwards. We'll see tomorrow. This has been Just Crust. I hope you all learned something because I sure as hell am trying to. And I'll see you all hopefully tomorrow.